picture that we'll come to of two black holes colliding, making these waves that are going out, and the black holes in the picture aren't very black, as you see. And we're going to go on from that. But I'm going to start going back from the beginning of what we know about gravity, what we learned about gravity as young students or even elementary school kids. And it became a scientific subject, I'd say, at the time of Newton. And Newton introduced his theory of gravity in 1687 in a book called the Principia. And that book, basically, he introduced what he called not just explain what gravity was, which obviously people had experienced gravity before, but what he called universal gravity, which is summarized by the equation that I show up here. And that is that if I have two massive objects, they'll attract each other always, proportional to the product of the masses of the two objects, and inversely proportional to the square of how far apart they are, and some constant that represents the strength of the interaction. Newton introduced the equation, but did not have was not able to tell us what the constant G is of the strength, which was done later, as I'll point out. So, okay. So there was a lot known, of course, before Newton, but what he did was he realized that the same physical laws that operate on the Earth operate everywhere. So that was kind of the universal aspect, one universe. He discovered the laws and motion of gravity that explained what we had before empirically, and that is Kepler's laws for planetary motion and so forth. And of course, Newton did a lot else. He did explanations of light. The first reflecting telescope brought us how to use calculus to do physical calculations and so forth and so on. So I'm just going to pick on the one part, which is his theory of gravity. Newton had introduced to us three laws of motion. And just in simple-minded terms, let me remind you what they are. Newton's first law of motion was that an object that has a constant velocity will keep a constant velocity unless there's a net force to change its speed or its direction. So my little picture here is just a spaceship, needs no fuel to keep going in space. As long as it's in space, it just keeps going. So if you have a constant velocity, unless there's a force, it'll keep going. That's the first of three laws. The second law is the famous force equals mass times acceleration, which basically in the picture here of someone throwing a ball, in this case an American baseball player, the ball feels a force as long as it's moving in the arm of the pitcher who's throwing the ball. But once it's released, it doesn't change direction or anything except by, for example, friction from the air, resistance of that type. Otherwise, it goes wherever it was going. That's the second law. The third law is that for every force, there's an equal and opposite reactionary force. And a picture of that just pictorially is a rocket ship, where the rocket is propelled upward by a force equal and opposite to the force of the gas, the burned fuel, expelling out the back. And that's Newton's three laws in kind of picture terms. And this is his universal law of gravity, which I said before. The attraction is directly proportional to the product of the masses and inversely proportional to the square of the distance, and G is yet to be determined. I'll come to that. He also, in the Principia, actually did the calculus to show that what I've drawn here is from the center of these objects, or the center of mass of the objects. But he did the calculus to show that that's that you just need the center of gravity are calculated from all the masses that are distributed for a finite mass object. Okay, so his three laws then explain a whole bunch of disparate phenomena. First, the eccentric orbits that comets have. Second, his law, so these are all why we use the word universal, to explain the funny orbits that comets have, which aren't in a circular orbit, or elliptical orbit. He explained the causes of the tides and how they vary in the ocean. He explained the precession of the Earth's axis itself, the fact that the Earth wobbles and has a precession, the perturbation of the motion of the moon by the gravity of the sun. Look, these are all small effects, but they're all basically explained by the same formulas that we gave here, which is Newton's universal gravity. So basically, Newton, when he brought this forward, solved most of the problems in astronomy or in terrestrial physics that were basically came from Galileo or Copernicus or Kepler, and he unified the whole thing. So this is, in some sense, probably the most impactful theory of physics ever introduced, was the simple theory of gravity by Newton. And not advancing. Okay. Second thing that I just wanted to the side, because it's very important, is that in the same volume, Newton introduced something else. He introduced basically what we call the scientific method. And this was new at the time. How do you basically analyze a problem and solve a problem and know that you, how confident you are that you have the right answers? And that was written down also in the Principia. So the Principia writes down the scientific method, which I'm going to go through a little bit right now because I think it's one of the major problems that we have in society, is that if our populace understood the principles, not the steps, of the scientific method, we'd have much less problems with fake news, alternate news, people not accepting the problems of polluting the atmosphere or anything else that basically we have because we don't analyze it. The principles as stated in the Principia are, first, that we are to admit no more causes of natural things, such as are true and sufficient to explain their appearance. The English is a little different than we write in the modern day, but basically you can only make a conclusion from something that you actually know or observe. The same natural effects must be assigned to all the same causes, meaning you have to be consistent in how you apply the answers. The qualities of bodies are esteemed as universal, so once you get an answer, that's assumed to be true, universal, and not just a special case. And propositions deduced from observations of phenomena should be viewed as accurate until other phenomena contradict it. These simple pictures are a way that we use basically to analyze. This doesn't really advance like it's supposed to be.
It's one slide in advance, actually later than you.
How do I do it? Okay. It's erratic. Okay, so these 4 rules are basically what Newton wrote down, and it was truly revolutionary at the time because it gave a way to look at information and draw conclusions that you knew whether those conclusions were valid or not. And basically, Newton went further than just outlining these rules and the reasoning for them. He actually described how they might be used to apply them to solve any given problem. And this analytical method is what I claim is something that if we don't teach the steps, we should be teaching in schools, because people would then, whether they do science or something else, would be better able to analyze what they read, what they hear about any of the problems that we have in society. So this analytical method that he invented far exceeded the more philosophical and less scientific ones that existed before by people like Aristotle or Aquinas. And what he wrote down then, he talks about, when you read it, about natural philosophy, which if you change it to the physical sciences, is basically what we use today. So it's just a difference in the word. And what he said is, as in mathematics, also in natural philosophy, which I'm saying is the physical sciences, the investigation of difficult things by the method of analysis ought ever to precede the method of composition. In other words, do the analysis before you make any conclusions. And that carries through basically to determine how much of a conclusion you can make or not make. Okay, back to the problem of gravity. So we have this law that was given by Newton in 1687, and it basically survived until Einstein came along more than 200 years later. And let me trace the history in between a little bit. Okay. Interestingly, I gave the equation there was one unknown. There was the strength of the gravitational force itself, capital G, which Newton couldn't tell us. And instead, it was determined 100 years later. And it was determined by Henry Cavendish. Henry Cavendish was kind of very wealthy and isolated British scientist who inherited a fortune and then used it to do scientific experiments. So he's responsible, for example, for the discovery of hydrogen. He wrote a paper in 1766, this is 100 years after Newton, called the Factious Airs. And in that he addresses inflammable air, which forms water, and as a result, combustion. And later experiments were done that showed this. So he was first well known for understanding what air is made out of, nitrogen and argon, and that there's oxygen, and how it burns, and so forth and so on. Then he took on a different problem, and the problem that he took on was trying to weigh the Earth. What's the mass of the Earth itself? And in doing that, he determined, as a side product, if you want, this capital G in Newton's case. So what he did to try to determine the mass of the Earth was use what we call now a torsion balance. That is a stiff rod that's vertical, and two horizontal rods with a little mirror that you can see up there. And the little mirror is used to reflect light, that you can see any little bit of movement in the torsion bar itself. So here's the little mirror. And then there's a sidebar and two heavy weights. And those two heavy weights are about, about 1,000 kilograms each. So they're big heavy weights on the ends, made out of lead. And from that, he then moved up two weights and watched the attraction. If he brought a weight near here and a weight near here, it twisted this a little bit. He measured the amount of twist, and from the amount of twist, he determined the mass of the Earth, which he got to be 5.9725 10 to the 21 in his units, which were British tons. And from that, once you know the mass of the Earth and you know the trajectories, then you can immediately determine G. interestingly, although no one had determined G in 100 years after Newton, he got an answer of 6.75 10 to the minus 11 in the units that we use, Newton meters squared per kilogram squared. And the best measurement today is pretty consistent with that. So he was tremendous in the sense that now, many years later, oh, I don't have it here. The measurement, of course, has more accuracy, but basically he, after 100 years of not knowing big G, he determined it with his method of torsion balance to pretty good accuracy the very first time. So 100 years after Newton, we knew the last piece of his equation, that is the strength of the interaction from Cavendish. This then enabled, over the period of 100 years or so, an enormous amount of consistent use of Newton's equations, and is incredibly impactful in terms of understanding science. For example, it explains immediately the planets going in elliptical orbits. The planets are arranged in an elliptical plane. The planetary orbits are slightly elliptical, but very nearly circular. Planets and the sun revolve and orbit, all of them west to east. The planets obliquely tilt their axes, but the tilts are very small. So as the planets go around, they have a slightly tilted axis, but it's very small. These are just all the features. The planets themselves differ in composition. If we look at the planets nearest the sun, they tend to be rich in dense metals. If you look at the planets further out, they're more hydrogen-like as you move to the planets that are further out. The meteorites, which we all know about, are different chemically and geologically from the planets and the moon. The rotation rate of the planets and the asteroids are all about the same. Rotating is hours, like somewhere between 5 and 15 hours. The planets, I don't have that. The planets distances from the sun obey something called Bode's law, and I'm going to come back to that. It's an empirical law, but it's part of the story I want to tell to get to Einstein. So the planets, their distance obeys a law that somebody put forward named Bode's law. The planet and satellite systems, all of them, resemble the solar system. And then there's other features. There's the Kuiper belt of comets, there's the Oort cloud, and finally the planets, 99% of the solar system. The atmosphere is in 99% of the solar system, and the mass is 99% in the sun. So with all that, it's just a very quick statement of what the solar system is. I want to concentrate on this empirical formula, which let me get to. Okay. So planets move around the sun in an orbit that's affected by the sun's mass, and to a lesser extent by other bodies in the solar system. That seems obvious. The laws governing the planetary motion were formulated by Kepler, but they're based on Gray's observations. And that brings us to Kepler's law. So we've got 3 laws of Kepler's, which I want to review before I get to this phenomenon that affects where we start having problems with Newton's theory. Kepler's law has 3 laws. The planets have elliptical orbits with the sun at one focus. The second law is as a planet orbits, a line connecting the planet and the sun sweeps out an equal area in equal times. I'm going to show you each of these 3 in a second. The square of the orbital period is proportional to the cube of the semi-major axis of the orbit. So those are the 3 laws that Kepler gave us, and let me show you that those are basically true. First, this is a picture of the first one. That is, if we have a planet, it goes around the sun in an elliptical orbit. That elliptical orbit is the focus of one of the two foci of the ellipse is the sun itself. It goes down around in an elliptical axis where the closest point to the sun is called the perihelion, and the point furthest away on this side is called the aphelion. And the average of the aphelion and the perihelion is what we call the semi-major axis. So this is the first law of Kepler, and something that was recognized as soon as, to be consistent, as soon as Newton wrote down his laws, and that is that you get elliptical orbits. And he explained the elliptical orbits. So this is the elliptical orbit. The sun sits at one focus. The second statement of Kepler is that you're going to sweep out an equal area in an equal time. And what I do is quickly show you that here. If the angular momentum of the planet is given here, and we sweep out an area across here, delta A, then the rate at which it changes is 1/2 r squared times delta theta delta t. That's in my notes. I'm going a little bit fast because we lost time. And the magnitude of L is given here, mr squared d theta dt. If I put that together, I get that the change of area with time is just the size L over 2m, which is just numbers, and that's a constant. So you get a constant sweeping of the angular momentum. That's the second law of Kepler. The third one starts to be more interesting in terms of where I'm going to go. The square, this is very empirical, but it's Kepler's law. The square of the orbital period is proportional to the cube of the semi-major axis of the orbit. And that's shown here. And if I put the planets on a picture of that, you can see they lie along a straight line. So we have this empirical rule of Kepler's, that the square of the orbital period is proportional to the cube of the semi-major axis, and we see it in this picture here, all the way out to Pluto. Okay, now I want to return to one feature of this, which is what I need to kind of start to show where we start to get some indications of maybe some differences from Newton's law. And this is another empirical law, and much of science is done by either developing some theory from scratch, from theoretical ideas, or starting from something that's more empirical and then trying to understand theoretically where it comes from. In this case, what I'm showing you are some theoretical models. So a law was put forward, which is empirical, called the Titius-Bode law, which is that the semi-major axis of a planet's orbit varies as 0.4 plus 0.3 times 2 to the nth power, very funny little formula. But if you take that, then this is what n would, starting from the Earth, this is what n would be. And the Earth is in here, and so it goes 1, 2, 3, 4, 5, on Mercury, which is closer than the Earth. Then if I take this formula, you predict this, and this is the accepted answers, and you can see that it agrees with this formula. Okay, people can develop formulas, and that's fine, and all the data fits. Usually the problem is whether something new fits that formula. And in fact, the first test of this happened in 1781 when Herschel discovered another planet called Uranus. And the distance when you take Uranus, then test this model, and I show it here. So it's n equals 6, the sixth planet. It's predicted to be 19.6 by this formula, and it comes out 19.2. So this law worked fine for Uranus, and that's where we stood. No violations anywhere as we entered the 19th century, the early 19th century. So at this point, that's what we knew. And then this law was used to predict another planet, which would be between Mars and Jupiter. And it turns out there is not a planet between Mars and Jupiter, but there's an asteroid belt between Mars and Jupiter. So that wasn't a violation either. So Uranus fitted the law when it was discovered. And I want to come to the last planet because the way it was discovered and its history leads to the problems with gravity that introduced us to Einstein. So Neptune itself was discovered in 1846, and there's a story that goes with that discovery. That discovery was made independently by a French astronomer or mathematician, Verrier, and a British astronomer named Adams, and independently. And it was done to explain a deviation in the predicted orbit of Uranus. So Pluto, which I'm not going to talk about, I think everybody knows it's always been debatable whether it's a planet or isn't a planet. It doesn't obey it doesn't fit the relations that we have anyway. So it's not considered a planet, but it's not the subject I want to deal with now. I want to deal with Neptune. So in the case of Neptune, if I can make this advance. Okay. So there were two individuals, this often happens in science, completely independent of each other. They didn't know each other. One was John Adams, a British astronomer, and the second was Urban Le Verrier. And after the discovery of Uranus, each of them in different ways noticed that Uranus didn't exactly obey Newton's laws. And it was there were therefore two possibilities. One is that Newton's laws weren't quite right, and I'm going to come back to that for Mercury in a little bit, so I'm introducing this first. One is that the laws of Newton finally aren't valid somewhere, and that was one possibility. The second is that maybe there's not all the information we have about all the planets. And Newton was first observed by taking the latter as a hypothesis and then an analysis by Adams and Verrier. So each of them more or less inverse engineered the problem of the orbits of the planets that they saw and asked what was missing to make that planet, the orbit of the planet Uranus, consistent with the laws of Newton. And the two of them independently did this. Verrier was the more successful of the two initially and dramatically because he actually sent a message to some astronomers, gave them the time to the message to get there. This was from Paris to Berlin. Told them to look up at the sky and where to look. And within 1 degree, they found the planet Neptune. In contrast, Adams had made the same prediction, but the astronomers that looked in his case didn't respond quite as well. So Le Verrier basically predicted Neptune along with Adams. He was better served and became famous immediately because it was seen. And in fact, a big controversy developed. The controversy developed because there were two of them that got this. Verrier became very famous for the discovery of Neptune immediately. He received many honors, including the Copley Medal, which is the big medal in Britain, given to a Frenchman once a Brit had done the same thing. It was discovered after that Adams had, because it's all documented and published, that Adams had already done essentially what Leverrier did, and they gave a second medal to Adams later. So this is the dispute. It's interesting, there's other history in this. Galileo actually saw Neptune, but he didn't see it long enough to actually make the discovery. So he saw it in 1613, but because of cloudy skies, he didn't see it enough days to see that it had a peculiar orbit. So it was left to be done this way. Okay, now we come to the beginning of the story of how and what existed at the time of Einstein to maybe make a new theory of gravity. I've given you a quick story of how successful the theory of gravity of Newton's was, and haven't given you any motivation for why someone would want to create a new theory of gravity. Experimentally, the only deviation that existed at the time of Einstein from Newton's theory came from another planetary one, which was discovered a little bit later, and that is the orbit of Mercury around the sun. I'll remind you that Mercury is our planet closest to the sun, and its orbit is highly elliptical, kind of like the picture shown here. And the distance between each time it goes around, you can calculate from the gravity from all the objects in the solar system. And if you calculate it, which was done in the mid-1800s, if you calculate it using Newton's equations, you get 532 arc seconds per century, and the actual observation is 575 arc seconds per century. And that was learned in about 1850. Neptune was discovered by Leverrier and Adams in the 1820s, so this is like 20 years later. Not surprisingly, Leverrier, who had been so successful with Neptune, immediately did the same analysis with Mercury. So he did a reverse engineering analysis and asked what was missing in order to give this. And he predicted that there was another missing planet. And that planet he called Vulcan. And that is that he will put a planet of some mass between Mercury and the Sun. This would be the planet that would be the most or he gave it a name, he called it Vulcan. And he made this proposal in 1859. After that, there were several claimed discoveries of Vulcan that are in the literature, but then they were basically disproven later. So by the time Einstein came along, this discrepancy still existed. In other words, the fact that Leverrier had predicted that there was a planet between Mercury and the Sun, or possibly a planet between Mercury and the Sun, there was no evidence that such a planet existed by the time of Einstein. However, it wasn't totally put to rest. You never can put something totally to rest. And in fact, NASA had a mission many years after Einstein looking for matter between Mercury and the Sun, and they set a limit that there's nothing, no series of matter or a planet larger than 10 kilometers in size. So rather small. So nothing even later was ever found. The only point is that this story, by the way, is told in a treatise by a little book, which I give here, which you can read, which is kind of interesting. And it's been reinvented for a television series, but otherwise Vulcan doesn't exist. Okay. So that's the history before Einstein. And what I'll do next, only we'll take a short break first, is point out some of the places where Newton's theory doesn't work, and which maybe motivated Einstein. It's hard to believe that Einstein was motivated by this problem of Mercury, but some people say that. But there's a series of reasons why Newton's theory is incomplete and motivates what Newton does, and I'll do that after the break.